Hello guys and welcome everybody. Today we're going to start talking about a new topic in chemistry which is about moles. Before we go there, let's start describing something that is related to our topic. As we can see here, we have a basket of orange. At this point, I can describe the quantity of this basket of orange in terms of mass. So I can say the mass of these three oranges, let's say, is about 1 kilogram. So I can represent this in term mass. Also, I can represent this amount by term of one basket in term of like a volume, like the basket here. In addition to that, I can describe this quantity in term of count, in which I have 3 oranges. So we can do the same thing in chemistry. We're going to introduce you to the new concept, which is called mole, M-O-L-E. And the mole in chemistry have a good description. We just noticed that in chemistry, we have atoms, and we could have molecules or ions. So if I want to represent a certain number of atoms, molecules, or ions, I can say there is a rule in chemistry says each 1 mole of any material, let's say whether it's an atom, whether it's a molecule or ion, it contains this huge number 6.02 times 10 to the power 23. And this number here is called Avogadro's number, and it refers to the scientist who proposed this idea. Generally, if we look at this number, actually, it's really huge. So if we have, for example, like 1 mole of water, like H2O, then it indicates that we have 6.02 times 10 to the power 23 molecule of water. And you just can imagine this huge number. We're talking about this number and plus 23 zeros, okay, which is really huge number in this case. Let's say you have 1 mole of helium, which is a noble gas, then it contains 6.02 times 10 to the power 23 atom. Okay. But the problem here, or let's say the question, why did I say atom here and molecule for water? We can say, for example, it depends on knowing the identity, or let's say the nature of the element or the compound that you have. For example, if I give you CO2, you have to put in your mind CO2 is a covalent compound, and actually it appears as a molecule in nature. And if I say sodium, let's say sodium, and actually you have to put in your mind it's an element, actually it appears as Na. Okay, so we can say sodium atoms. It doesn't appear as a molecule in nature since it's a giant structure. Let's take some examples. If I ask you if you were given, let's say, 0.340 mole, okay, is it okay to have a mole that is in decimal number? The answer is yeah, sure, you can do it. If you have this moles, Al2O3, for example, and the question is how many molecules of Al2O3 are in this amount of moles. So the first thing you should put in your mind is writing and remembering the formula, which is 1 mole of any material that contains 6.02 times 10 to the power 23. At this point, you have this ratio. Is the number of moles given to you here? Yeah, actually it's in here. So we can take it and just put it 0.340. And since you don't know actually the number of molecules, you can put X in here. At this point, how can I do this equation in here? You can multiply the 2 numbers that are in front of each other and then divide them over the number in here. So we can say X times 1 mole equals to 0.34 times 6.02 times 10 to the power 23. And then the value of X is equal to 2.05 times 10 to the power 23. Molecule of Al2O3. And now the question is, I calculated the number of molecules of Al O3. I have the molecules. I have this huge number of Al2O3. If I want to make an extra step and ask you like how many how many atoms of Al in an Al2O3 that is given to me in here. I just want, let's say, to make another branch for this question. All right, so there is a rule says, now you can say, if you look at Al2O3, each one molecule of Al2O3 contains 2 aluminum atoms. How many Al2O3 you have here? I have this huge number in here, which is 2.05 times 10 to the power 23. And if you just make some calculations, you multiply these two numbers together, and this one here by 1, you can say x times 1, which is in here, equals to 2 times 2.05 times 10 to the power 23. The answer is going to be 4.09 times 10 to the power 23. Okay, atoms of Al. And if I want to extend this equation furthermore, I can say how many oxygen atoms. We can do the same thing here. We can say each 1 mole of Al2O3 contains 3 oxygen atoms. How many Al2O3 I have? I have this 2.05 times 10 to the power 23, and just put x here. X equals to 6.14 times 10 to the power 23 atoms of oxygen. Let's take another example. If you were given 2.5 times 10 to the power 23 molecules of C6H12O6, which is the glucose, the question is how many moles of C6H12O6? I'm asking about the number of moles. All right, since you're given the number of molecules and the question is asking you about the number of moles, we just can remember that golden relationship, which is Avogadro's number. And we can say each 1 mole contains 6.02 times 10 to the power 23. And since the number of moles is unknown to me, I put x under moles and just write the number of molecules 2.5 times 10 to the power 23. And just make a cross multiplication at this point. All right, so we can say x times 6.02 times 10 to the power 23 equals to 1 mole times 2.5 times 10 to the power 23. And then we can, in order to make some calculations, we divide over 6.02 times 10 to the power 23 in order to keep the x alone. And then here we do the same process, 6.02 times 10 to the power 23. And then the answer is going to be 0.415 mole of C6H12O6.